Hello once again, class, and welcome to another mock lecture. Today we're going to be talking about the factor theorem. Now, in the last video about division and synthetic division, we talked a lot about the division algorithm, which is that you can write some number called a dividend equal to some divisor times a quotient plus a remainder. We then applied that to polynomial stuff, so the dividend was probably some polynomial function, the divisor was also some polynomial function, and we got some quotient and a remainder when we did that long division. Well, today we're going to talk about two specific things regarding the divisor and the remainder. But first, what I did here is I just changed the notation for this stuff. The dividend is some f of x function. We're going to call the divisor d of x, the quotient q of x, and the remainder some r of x function. So every single one of these things is in terms of the same variable. But our divisor today is specifically going to look like this. It's going to be a linear divisor that has a leading coefficient of 1. Now, if you're thinking, now hold on, that actually sounds familiar. Well, that's the type of divisor I taught you how to use synthetic division with. So that's good. Today we're going to be talking about things that are allowable for synthetic division. Now, because we're dividing by a linear divisor, we know that we're going to get some number r as the remainder. So it's actually not going to be some function that's in terms of x. It won't have x in it at all. It'll just be some kind of number, because that's what happens when you divide by a linear divisor. This value that we end up getting, the number that's the remainder, ends up actually being the function evaluated at k, at this k right here. That's what you end up getting as the remainder. To see that, right, let's say that we have this, f of x is equal to some linear divisor, x minus k, times q of x, and then plus some remainder, right? Let's plug in k for x. If you plug in k for x, this thing becomes k minus k, which actually then becomes 0, because k minus k is going to be 0. Well, then you have 0 times q of x, and then that whole thing is just going to be 0, because anything times 0 is 0. So you get f of k is equal to r. That's the worst box I've ever drawn in my life, but there you go. You get f of k is just straight up equal to r. And this is a theorem. It's called the remainder theorem. It says if a polynomial is divided by some x minus k divisor, then the remainder is straight up f of k. It's the evaluation of the function at the value k, which means that you can actually evaluate f of x using division, which is kind of hilarious, right? If someone says evaluate f of x, and it's this long quartic function at x is equal to 2, I think like most algebra students will just plug in 2 to the function, right? And you can pause it here to see that I did my math correctly. But you plug in 2 to all the x's, you end up getting this number 25. Well, instead of that, you could actually just do the synthetic division with 2 as the thing that's in the box. And if, again, you can pause it here to check my math, but I just did the synthetic division, and again, I ended up with 25. So evaluating the function at 2, which is f of 2, gave me the same thing as when we did synthetic division. Our remainder was the same thing as the evaluation of the function. So if you wanted to, you could always just evaluate by using synthetic division for polynomials. This is strictly for polynomials. Anyway, I replaced r then with f of k. Notice that, right? This was an r before, so now our division algorithm kind of looks like this. So this is the type of thing that we're going to be focusing on for today, specifically when that thing is 0, when f of k is equal to 0, when the remainder is equal to 0 after you've synthetically divided x minus k through the function itself. Okay, which means that's just gone. What that means is that this linear divisor has to be a factor of f of x. All right, so let's talk about the factor theorem. It leads directly into the factor theorem. It says that a polynomial f of x has a factor x minus k if and only if one of the following is true. So I'm about to put a list of things here. If even one of them is true, every other bullet point, and more importantly, this is true. Okay, the first one is that there's an x-intercept at x is equal to k. If there's an x-intercept at k, then we know x minus k is a factor. All right. The second is f of k is equal to 0. As we just discussed, this is kind of part of the remainder theorem. If the remainder is 0, well, then x minus k has to be a factor of f of x. And then the third one is just kind of a reiteration of that, which says that x minus k divides f of x evenly. If any of these things are true, then all of the other ones are true, and also x minus k is a factor of f of x. So to see how this all works, suppose that we know m of 1 is equal to 0. For some m of x function, this is quadratic x squared minus 3x plus 2. Okay, so we're given this one, right? This is what we know. M of 1 is equal to 0. Well, so what else do we know? Well, first we know that there exists, and that's what this little symbol means, by the way, the backwards capital E, there exists an x-intercept at x is equal to 1. Okay, so we know this one. We know this purple arrow up here. We also know that x minus 1 should divide m of x evenly. But the most important thing that we know from this, just by given this, just by knowing that when you plug in 1, you get 0, we know that x minus 1 is one of the factors for m of x. Okay, and now it's actually verifiable. I mean, this isn't that hard to factor. The two things that multiply together to give you positive 2 and add to be negative 3 are negative 2 and negative 1, so this is just the way that you factor it. So that's a lot that we know from just m of 1 being equal to 0. Like, that's all we're given, and now all of a sudden we know one of the factors for this thing. That's a super powerful thing to say. Let's look at a few more examples to really get the gravity of what we're saying here. All right, example number 1 says, consider the graph below. There's a few things that we should be able to get from this graph almost immediately, right? The first one that jumps out to me is that it's got to have a positive leading coefficient because it's rising on the right and it's also falling on the left. It's probably quintic because it's got 1, 2, 3, 4 turning points, so it's probably a degree 5. And it also has 5 x-intercepts, right? So 5 x-intercepts, 4 turning points, that falls in line with our assumption of it being a quintic polynomial. Here are the x-intercepts, right? The x-intercepts are at negative 3, negative 2, negative 1, 2, and 3. Now, what that means by the factor theorem is that x minus these things represent factors for this graph. So what we're going to do is we're going to call this function q of x, and I'm going to show you kind of the factored form of what this thing is. Okay, we'll start from the bottom. Since x is equal to 3 is a 0, that means x minus 3 is a factor, right? Just by the factor theorem. Since x equals 2 is a 0, x minus 2 is a factor. Since negative 1 is a 0, x minus negative 1 is a factor, but since we're subtracting a negative, we might as well consolidate that and make it a plus. Since negative 2 is a 0, x minus negative 2 is a factor, or x plus 2 is a factor. And since negative 3 is a 0, x minus negative 3 or x plus 3 is a factor. If you know x-intercepts, then x minus whatever those x-intercept values are is a factor, right, of the polynomial itself. So we basically just, we know the whole formula for this thing. I guess the only thing that we don't know is actually what the leading coefficient is. The only thing we know in this case is that it is positive. But sometimes there are even ways that we can find exactly what that leading coefficient is. Here, there's not enough information for us to be able to tell, but we do know this. We do know that it's some positive value. Now, this specific form actually has a name. It's called the complete factored form of a polynomial. So it says, let f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way to a sub 1x plus a sub 0. That's just a polynomial. Be a polynomial that has n real zeros. So for now, we're restricting our types of zeros to real numbers, which means they correlate to x-intercepts. And we're going to list them, we're going to name them as C1, C2, C3, C4, all the way to however many there are, C sub n. And it's actually possible for some of these zeros to be exactly the same value. Like, for example, it's possible that both of these things right here are the number 2. But you want to list, in fact, you have to list anytime a 0 is repeated as many times as it is repeated. So if 2 was a repeated 0, you'd have to list it in the list of zeros twice for complete factored form to actually make sense and actually be the factored form of f of x. These types of zeros that repeat are actually called multiplicities, which I have a video on, right? You should go watch it. I have a video on multiplicities. But if that's the case, right, then f of x can be written in what we call complete factored form exactly like this. F of x is equal to leading coefficient, which is actually the same leading coefficient that you see in standard form, times x minus your first 0, times x minus your second 0, times x minus your third 0, times x minus your fourth 0, times x minus your fifth, sixth, seventh, all the way until you get to x minus your nth 0, and that is completely factored form. So if you take a step back and try and figure out, like, what does this mean? The TLDR version of this is if you know the zeros of a polynomial, you can factor it. Okay, it's mind-blowing stuff. It's pretty cool. You just need to know the zeros of a polynomial, and now all of a sudden you can factor that polynomial. Now, does this mean that you can completely forget about the whole thing where we were doing, what are the two numbers that multiply together to give me this, but add together to give me the middle number? No, but at least the game is changing a little bit, right? I mean, there's going to be cases where we don't have a graphing calculator, we're not going to be able to graph, and so we're going to still need to rely on some of the traditional factoring skills that we had, or even the quadratic formula at times, but the game is changing a little bit with this completely factored form thing. Now it's just find the zeros, and x minus whatever that is a factor of the polynomial. All right, so let's look at this example. Completely factor j of x, which is this quartic function, given that it has zeros at -4, -4/3, 3, and 5. So in this example, we know what the zeros are for this. Okay, so here's complete factored form. Our function is called j of x, so we should rewrite this as j of x, but we're going to start with the leading coefficient, which you can actually see what it is in the standard form. It's 3. So we'll say j of x is equal to 3. Then we'll have x minus our first zero. Our first zero is -4, so we have x minus -4, but x minus -4 is x plus 4. The second zero is -4/3, so x minus -4/3 or x plus 4/3. The next zero is 3, so x minus 3, and the next zero is 5, so x minus 5, and we're done. We just factored this polynomial. We knew where the zeros were, we put it in complete factored form, done. Right? Pretty cool stuff, right? We factored. All we needed to know was the zeros. For example number 3, suppose we don't know where the zeros are, so they're not given in this one. Well, that's fine. Just graph it. Graph the function. Now we know where the zeros are. They're at -3, -1, and what looks to be 1/2. So again, we toss it in its complete factored form. X minus -3 becomes x plus 3. X minus -1, right from this one, becomes x plus 1, and x minus 1/2 from this one here. I just put the leading coefficient out in front, and there we go. It's completely factored. Now for this one, let's say that you're only given one zero. So it says completely factor this cubic polynomial given x is equal to -1 is a 0 for this. Well, since we know it's a 0, we know that x minus -1 or x plus 1 must be a factor of p of x, right? And because we know it's a factor, that means that it has to divide evenly into p of x, right? This is all factor theorem stuff. Well, if it divides evenly into p of x, let's divide it. Let's divide p of x by x plus 1. Let's put -1 in the box, right, for the synthetic division. And by the way, the reason that we're using -1 is because previously when we're dividing by a divisor, which we're dividing by x plus 1, because x plus 1 is the factor that p of x is divisible by, I was always like, oh, figure out what makes the divisor 0. So set it equal to 0, and then you subtract 1, so you get x is equal to -1. And that's what goes inside the box for synthetic division. Well, now I can finally say, no, it's just the x-intercept. That's what's going in the box, right? Those are the same thing. So p of x, we're using x plus 1 as its divisor. Let's figure out what the quotient is by doing the synthetic division. Okay, so I wrote my coefficients, 2, -2, -34, -30, and I'm just going to do the synthetic division here. 2 times -1 is -2, which added to -2 is -4. I just realized I lost my p of x there. Times -1 is +4, plus -34 is -30. Times -1 is 30, which when you add to -30 gives you 0, which we knew would happen. We should get 0, because we're saying here -1 is a 0, which means when you evaluate it, you get 0, which means by the remainder theorem, the remainder should also be 0. So this is the quotient that we end up getting when we use x plus 1 as the divisor. And now I'll just focus on factoring this thing. We could actually have graphed this thing at the beginning to kind of see, but it's important to have different strategies for how to do this. And also maybe we only get 1, 0 when we graph in the future. And that's going to be when we start considering complex zeros or imaginary zeros. So it's important to go over this and understand how this works, because graphing won't always give you all the zeros. But anyway, here we got 2x squared minus 4x minus 30, for which I'm realizing that I'll have a 2 in common. So I'm going to just take that out right away. And notice that the complete factored form is actually starting to take shape here. The 2 as the leading coefficient just showed itself in complete factored form. So that's where that comes from. Now we just need to factor this, which actually factors pretty easily if you know how to factor. So now we still need to factor this part. And again, you could graph this to see where the zeros are, since now we know the factor theorem, but again, it's important not to always rely on graphing. This is easily factorable if you know how to factor. There are two factors of negative 15 that add to be negative 2. It's negative 5 and positive 3. And so here you go, right? Here's the complete factored form. So you might be asking, well, what if you get here and then you can't factor this, right? And maybe even to take that a step further, you try to graph it and where it's intersecting is like some really weird decimal that you're not sure how to write, right, in its exact form. Or again, maybe when you graph it, it ends up looking like this. Then what are you supposed to do? This following strategy can still work for you. Let's pretend that we were completely factoring this thing. Again, we're given negative 1 is the 0. The coefficients are here are 1, negative 1, negative 3, and negative 1. And if you want to pause it here to kind of see how I did the synthetic division, feel free to do so. But like everything that we just did is also applying here. So when I write out b of x, this is our divisor, x plus 1. This is what I ended up getting as the quotient. But now notice we can't factor this easily. There are no factors of negative 1 that add to be negative 2. So it doesn't factor traditionally, but we're still about to factor this thing. And maybe when we graph this, in fact, you can try graphing this, it's going to have really weird intersection points. They're going to be decimals, right? So how are we supposed to write that? Because you don't want to round. Let's say it intersects at like 3.01249464, and then it stops because it's rounding it. You can't just do x minus 3.049. I don't even remember what I just said, but you can't do this because that's an approximation. That is actually not a factor of this thing, right? Not a factor. So what are we supposed to do? You just need to find the zeros a different way. And there's a guaranteed way to find zeros for quadratics. This is the quadratic formula. So let's say you get this. You use the quadratic formula, you get 1 plus root 3 and 1 minus root 3. So then x minus those zeros are going to be the way to factor this. So x minus 1 plus root 3 and x minus 1 minus root 3 would be the way to do that. So if this looks kind of weird, it's because it is. But remember that this is just a number. It's an exact number because we don't want to round it, but that would be one of the factors for this b of x function. And we'll talk more about this type of strategy in a later video once we start considering imaginary zeros as well. But for now, we'll stop. We'll stop here. I think that's enough examples to kind of get you started with completely factoring stuff using the factor theorem in complete factored form. If you guys have any questions, please leave a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.